talk is about superconducting qubits for adiabatic quantum simulations, in particular about controlled interactions with superconducting qubits. And that's a work in collaboration between Zurich Research, IBM Zurich, and IBM in Yorktown. And I should particularly point out that David McKay did many of these experiments. So the system that we are doing the experiments with is a superconducting circuit system using transmon types qubits. And the main goal is basically for the future vision is to do digital quantum computing, universal quantum computing with this finally error correction using Clifford gates. And so that's, we have already heard what you can do with it. But now everybody now figures out that it's a little bit a hard task in the near future to do. So we need to do something more for the near term, and that's adiabatic and an analog quantum computing, where you can do adiabatic dynamics, you use shallow circuits on this, you don't probably need error correction. And so using this kind of platform for all these different types, we need to somehow find out what can we do in terms of interactions, what kind of interactions can we introduce to the system to get, for example, to shallow circuits. So, and the basic requirement is we need to get 2 qubit gates and interactions in these systems. So let's have a closer look. What we have is a superconducting qubit of the transmon type. We have, as usual, the nonlinear Josephson junction making the qubit out of it. And the interesting thing is now that we get with this system a T1 and T2 of 70 to 100 microsecond. And it's because we are using the most simplest device that you can think of. It's just 2 electrodes which are connected via 1 Josephson junction. So it's a fixed frequency qubit, and that gives us no problems with flux noise and long T1 times. The second element on this chip is microwave resonators. And these microwave resonators are coplanar transmission line resonators, as you probably all know, or most of you know. And they serve different purposes. For example, as noise filters for readout of qubit state. But what I'm now interested in is how these are used for multi-qubit quantum buses, and how you can actually replace this element by a different element, which gives you more flexibility in coupling qubits. Something missing, okay. So what we have at the moment here, and there was sorry for this, the slides are somehow weird still. What I should again point out now here, you see that there is not so many tunable elements. The junction is a single junction, there's no flux tunability here, there's no flux tunability here, so how can we induce gates? And the gates that we are inducing is using microwave control. And how this is done at the moment is using the cross-resonance gates. And in brief, you have in the Hamiltonian that you write down, you have a CX interaction, so a controlled X interaction, if you drive this qubit via the first qubit. So you have a control qubit and you have a target qubit. If you drive now at the target frequency, the control qubit, you see that the Rabi rate of driving this qubit depends on the state of the control qubit. And that's this controlled X term here. So with this, you just have to wait a little while until you get either the qubit being in the ground state or in the excited state, depending on the state of the first qubit. So with this, you can make a gate. You can make a controlled X gate out of it. Typical gate times are 400 nanoseconds. Gate fidelity is 94%. But there has not been recent results also within IBM is that they can push the gate fidelities to 99% and about 160 nanosecond gate times by using more clever techniques in how to control these gates. But these gates have a little bit of drawback. And one of them is that the qubits must be closely spaced in frequency. And that's what's shown on this graph here. There is one region which is the good qubit limit. There is a leakage regime where you don't want to be, and there is a regime where the gate is just weak. And to be here means that the qubit has to be close in frequency, and that's a problem. If you want to scale the system up to multiple qubits, we cannot do this simply because due to the fabrication constraints, which give us approximately 5% or about 100 megahertz of a 5 gigahertz scale fabrication precision, we it's hard to get the qubits at the right frequency. So that's one type of problem. The other type of problem is that we only get the controlled X term. If we want to use this for analog simulation or adiabatic computing, we need more flexibility in the interactions. We need not only this term, but we also want to have other terms. In this Hamiltonian, you see there is CC terms, for example, but they are not easily controllable. So we need something else. So let's compare what we can get and how this compares to other qubit gates, what alternatives there are. So I just discussed the cross-resonance gates. The advantage is that we can use now fixed frequency qubits with long coherence and long T1 and T2 times. We can unfortunately not have low microwave drives. We have to use strong microwave drives, and the qubits have to be close in frequency. As alternative, we could now introduce flux-tunable qubits and use, for example, C-phase gates, CCs, which are relatively fast, which have a good on-off ratio. The drawback is that you suffer from 1/f noise, and until this problem is not solved yet, it will degrade our T2 times, and this is not what we want. The cousin of this gate here is the SWAP gate, so that's basically by tuning the qubits on resonance. Again, we need flux tunability, but it would give us a complementary interaction. It would give us this XX plus YY gate. There is also other gates, like geometric gates. They might be robust and they might be good, but at the moment they are all slow as well. So we want to have fixed frequency and long coherence times. We want to be relatively fast and on the order of the coupling strength between the qubits. We want to have a good on-off ratio, and if possible, we want to have different types of interaction at the same time. So what can we do? We can actually follow an idea which has been brought up by Patrice Paté in 2006 for flux qubits actually, and redesign our coupling element in between. So we still keep our qubits as a single junction non-tunable transmon devices, but we introduce now some flexibility in our coupling element. And that's now also recently in a different inductive version described in this paper by Elliott Capit, and also used in the Martinez group. So what we are doing here, we want to modulate now this J coupling, the coupling between these two qubits, and get to a time-dependent Hamiltonian. And this Hamiltonian is now written in this way, so we have this XX interaction, the interaction between the two qubits, which we can modulate in time. So what this means now, if we go to the rotating frame of the qubits and expand this cosine and add the terms to the sigma x interactions, so you see now I expand the sigma x in a sigma plus sigma minus term, and I add now the frequencies of the sigma plus and sigma minus here. So what I get here is a sum of terms where I get sigma plus, sigma minus, so that's the swap interaction, where one qubit excitation swaps to the other one. I get the plus plus terms, which means that both qubits gets one excitation and both lose one excitation. I get these terms from the cosine, and each of these terms has a certain frequency. So now you can easily see if I select now this frequency properly, I can get rid of some of these terms. For example, if I choose now the modulation frequency to be the difference frequency of the qubits, like here, it's only that the swap term, the sigma plus, sigma minus, is left, whereas these are oscillating so rapidly that I can easily detect them and adiabatically eliminate those terms. And that's what I described here. So this gives me now a certain flexibility in choosing this modulation frequency. I can now either take now the choice of frequency that I modulated at the qubit difference frequency as described here, and I would get a swap interaction. This corresponds to a XX plus YY interaction. I can also go ahead and drive the system now at the sum frequency, which is going now from the 0, both qubits in the ground state, to both qubits in the excited state. With this choice of drive frequency, of modulation frequency, I retain these terms, and that's just the blue sideband terms where I transfer both qubits into the excited state. And what I can also do is I can not only drive this transition here and this transition, I can also drive the 1, 1, 2, 0 transition. So either the double excited state to the 1 qubit in the second excited state. And that corresponds to then the C phase gate. And this gives me a CC type of term. And so with this type of gate, I can actually create XX, YY, and CC interactions at the same time by driving these different interactions. How can I do this? Now, one choice is you just insert here another transmon type system, or you can have an anharmonic circuit, something which is tunable in frequency. And so making this choice just gives me, again, this Hamiltonian. There is something missing here. Sorry for this. So what I do now, I have this other anharmonic system, this third ancillar transmon, and this changes in frequency. So with this change in frequency, I see now that my modulation term changes here, which should be here. And this modulation term is actually dependent on the difference between the tunable coupler and the qubits. So there should be a 1 over delta here, 1 over delta between delta frequency between the tunable coupler and the qubit, and tunable coupler and the second qubit. With this now, I can get a gate, the sigma plus, sigma minus gate, which can be up to 50 to 25 megahertz as a rough guess with typical numbers for the coupling strength. I can go to large qubit detunings. That means I can place them apart by gigahertz and not only by 100 megahertz or so. And I can also maintain the coherence because the T1 and T2 is only affected in second order. The qubits basically don't see this other coupling element if it's far away in frequency. And also during the gate, there is never a photon in this coupling element. It's only virtually populated. We did the experiment, and that's the sample. So you see here there's the readout resonators, there's qubit 1, qubit 2, readout resonator for qubit 2. There is this tunable bus coupling element in between, which has a SQUID loop, and the SQUID loop can be driven by a high-speed flux line. And what we get if we do the experiment, for example, the SWAP experiment, I excite qubit 1. I modulate the coupler for a certain time, induce this coupling here, and see that there is oscillations here. And I can extract now from the target state a state preparation fidelity of 97.4%. That's what we got now in preparing from the 1 qubit excited state, the superposition Bell state here. I can also do randomized benchmarking with forming a Clifford gate out of it. So we're doing an iSWAP. And from this benchmarking, randomized benchmarking, I get a number which is 98.2 for the interleaved benchmarking and 97.2 for the standard randomized benchmarking. So for this experiment, it's pretty good, and there's room for improvement in tuning the parameters properly to get more separation between tunable coupler and qubit. So what do we want now, for example, for analog quantum simulation or adiabatic optimization protocols? We have seen now that I can get now these 3 terms. What I want as well is actually tunability on the single qubit terms. And this I can get as well by driving the qubit. So I can go to a driven system, and by driving the system, I write down the Hamiltonian, that's the qubit sigma c, the qubit frequency. And in the driven system, I add now this X transverse drive interaction. If I go again to the rotating frame and write down how these translates into the rotating frame, I see now that by tuning the amplitude, the phase, and the difference between the drive, the difference frequency of the drive and the qubit, I can see that I can get to this Hamiltonian, where I can tune now the X, Y, and Z component individually by choosing the parameters of microwave drives. And here I can go easily between 0 to 50 megahertz in the parameter range. If I use now this protocol for adiabatic annealing, for example, I have to keep in mind that my dissipation now works in a different way. It does not go to the ground state, but it will go to a steady state. And that's probably an interesting physics problem, but just to keep it in mind. And that also means that whatever I do, I should be much faster than the coherence time. So what can this be used for? And for example, we can use this for simulation of molecules, adiabatic simulation of molecules. For example, the toy model of having a hydrogen molecule, like it's earlier shown, last year shown also in the Martinez group. I can go now to a different representation in terms of 2 qubits. It has been shown in our group that you can reduce this problem to a 2-qubit problem where you have these y terms, so the single qubit terms, and xx and yy interaction, which should be tunable individually. So we can now go ahead, start with a transverse field Hamiltonian. We can now go to this adiabatic protocol, driving the change in bus parameters adiabatically. I can have now the ability, in principle, to go to switch on simultaneously the xx plus and xx minus yy drives. That this works, that xx and minus yy drives we reject. We just have to do now the simultaneous driving. And then I can find out with this protocol the adiabatically going from the initial state to the ground state. And when doing now a numerical simulation and checking whether this can happen within the coherence time of the qubit, I find that I need approximately for a certain range of R parameters of radii of the H2 atom, I can find that I have to be faster than approximately 10 microseconds, and that's well within the coherence time of our qubit. Another outlook is I can use now for the CC interaction for quantum adiabatic optimization. So for driving this transition here, I can induce a phase shift onto the 1-1 term, and I can reject that this J term, so this CC interaction, we can get up to a similar strength than this interaction. And so this should be useful then also for quantum adiabatic optimization problems. Another thing I want to mention here, that this bus architecture or this bus design can be extended, and it's also a nice thing is you can not only couple to 2 qubits at the same time. You can also imagine that you have now more than 2. For example, here it's shown 4 qubits. You can have 1 coupling element, and because now all these transitions that I discussed are driven via frequency selection, you can drive now between different qubit frequency, you can drive selectively interactions between the different qubits. And this could be useful for looking into spin qubit lattices with nearest neighbor coupling, and it could be useful for the parity adiabatic quantum computing architecture, where we would need a 5-way coupler, and this will be discussed in the talk by Wolfgang tomorrow. So with this, I come to the conclusion. And so what we have is a tunable coupling gate, which retains the long coherence of our rotating frame qubits. It provides us with stochastic and non-stochastic xx, yy, and cc terms. It is controllable in amplitude, phase, and frequency. It is fast, relatively fast, of the order of the J-coupling strength between the qubits. And we get high fidelities at the moment, which is 98% randomized benchmarking for the swap gate. And this can be useful for as a tunable interactions for quantum analog adiabatic quantum simulations and computation, but also for gate primitives in surface code quantum computing architectures. And with this, I want to thank you for your attention.
Question?
For the 98% randomized benchmark, what was the time of the gate? I missed that.
About 150 nanoseconds.
Okay. And what were the coherence times of the qubits?
In this case, it was 30, T2 was 30 microseconds,
okay,
approximately, and T1 was, I think, was 50 or so. So in this, so it was a little bit lower than the standard qubits, and that's because the coupler was still hot. So there is room for improvement in this, but in principle, it's the same.
It's quite good. Yeah. The other question I had is going back to the recent result from the Yorktown group with about 99%.
Yeah.
That was because they got the qubit frequencies close to each other. they were able to make it fast and accurate. Is that correct?
So it was, the main thing was for the cross resonance you need strong microwave drives. So there was not a sample, was that you had a direct microwave drive there, and then you can actually have the power to drive the gate, but then you have to worry about all these other terms, like the CC, IC, and CY, and all these terms. And then you need to introduce compensation drives, and
so they got it all compensated, right?
You have to be able to compensate this and know what the system does. So that is the
for that gate. Do you know what the off coupling was? Because that's an important figure of merit too.
It was, I think, of the order of 100 kilohertz to a megahertz. So it was because the qubits were close. It is there. I mean, that's the on-off ratio, which you cannot avoid because you have the qubits to be close in frequency. Yeah.
Thank you.
Yep. Oh, here.
So you're proposing this hardware to do quantum annealing, in a sense, right? For quantum
that's what you could do with it. Yeah.
So, but all the interaction you were getting for tunability and interaction with, you were driving the system. So are you proposing to do annealing in some rotating framework? Okay. I think there are many open questions need to be answered for that kind of work.
Yes, I agree.
Anyone else?
Yeah, so you get these stochastic and non-stochastic terms, but this is achieved by the single drive of your coupler. So how tunable is this ratio between all terms?
Since all of them are different, so you can drive the coupler at different frequencies, and basically the amplitude to which you drive the coupler tells you about the ratio of the coefficients of the XX plus YY or the coefficients of the XX minus YY. So in principle, you have tunability over all these components simultaneously.
But it's not just amplitude; it should be also some other parameters.
And phase. I mean, you can also make them plus minus. So in principle, you can tune them as you wish.
Okay, thank you.
One last question, anyone?
Just quickly, with the four-way coupling, have you considered whether you're going to get noise on all possible pairs of qubits when you have that geometry?
Noise in the sense of crosstalk or noise in the sense of stochastic noise?
Either one.
I think crosstalk will be an issue, because if you're driving the qubits, you will off-resonantly drive other transitions, and then you have to be able to avoid transitions or being able to calibrate it properly. So, and that will tell you about how you have to space your qubits, and this will tell you how many qubits you can actually put onto the same coupling element.
Okay, thank you one more time.